All right, so this is where we finished off last day. We were talking about milliequivalents, and we were talking about how to calculate them, and we are talking about how to use them to make things like bar graphs, and we were talking about balancing, looking at the balance between the ions and cations and all that. So I thought before we got into any more information, we would just do a quick review problem. So here's a question. You can see there's some water analysis information there, and it says draw a milliequivalent per liter bar graph and list all hypothetical combinations. So that's what we're going to do. So here's the question. Usually the questions will have the data analysis, and I usually like to put it in a table and give you information such as the equivalent weight. So remember that to calculate the milliequivalent per liter, equivalent per liter is equal to the milligrams per liter divided by the equivalent weight. So basically, you're going to take these variables here and you're going to divide them. So 94 divided by 20, 24 divided by 12.2, and so on. And I'll even leave you some space in the table so that you can throw those numbers down. So that's what you're going to get with these values. So you're going to get for calcium 4.7 milliequivalent per liter, magnesium 1.97, and so on. Okay, so to make the bar graph, remember it's pretty basic. What you're going to do is set some sort of scale. So I always recommend 1 centimeter is 1 milliequivalent per liter, and you make your bar graph. So that means, for example, the calcium is 4.7 milliequivalents per liter. So you can make your bar to represent calcium be 4.7 centimeters. Magnesium is 1.97 milliequivalent per liter. So you're going to add basically 2 centimeters onto that. And when you add 4.7 plus 2, that's going to equal 6.7, which is why I have the 6.7 label right there. And then when we get to the end, the sodium is on the end. So usually you put these in order of, size, right, in terms of quantity. And you're going to group the cations together, you're going to group the anions together. One thing I noticed I forgot on this was labeling my 0. So there's my 0 on my axis. And it's going to look something like that. So use a ruler, make it neat and tidy, and it should be an easy couple of marks for you. So the other part of the question was, if you go back to the question just on the previous page, it said list all hypothetical combinations. So that's what I'm doing here at the bottom. So remember, the hypothetical combinations is basically looking at which anions, or how the anions fit with the cations to make various compounds, right? So for example, calcium, we can pair calcium with all of the anions. So we're going to have calcium bicarbonate, calcium sulfate, calcium chloride. And so if I ask you this kind of thing on a test, just keep in mind, I could ask you to give me the chemical formulas. So that would be here, or I could ask you for the names. So for example, CaCl2 is calcium chloride. So if I'm specifically asking you for the name, make sure you give the name. If I'm specifically asking for the chemical formula, make sure you give the chemical formula. If I don't ask, you can give me either, right? If I'm not being specific there. So you can imagine that for magnesium, it's very similar. Magnesium bicarbonate, magnesium sulfate, magnesium chloride. And I can do the same thing for sodium. And just if you're doing the chemical formulas, make sure you get the stoichiometry correct. Like I said, this is relatively basic kind of introductory chemistry stuff. So hopefully that makes sense. So this is not the end of milliequivalents. What I want to do now is talk about water hardness. And you're going to see that the calculations for milliequivalents actually are helpful in determining water hardness. And water hardness, by the way, is the topic of lab 1 that we're going to do tomorrow. So I really like it when the labs and the lectures kind of line up. So let's talk a little bit about water hardness. And that's going to be about probably at least half or a little bit more of today's lecture. So water hardness, it says here, is due to multivalent metallic cations. So what does that mean? Multivalent means it's going to have a charge of greater than 1. And since it's metallic, it's going to have a positive charge. So the reality is, when we're talking about water hardness, it's mostly calcium and magnesium. Those are the two that are always found in the most abundance, at least in kind of natural water samples. There may be other things you might see in labs or industrial processes. They're going to have a different variety of ions. Some other ions that can contribute are iron and manganese. Usually in terms of the quantities, iron and manganese, kind of, if you look at significant figures, they're kind of way out there, right? So you're looking at the 99.9% of the hardness is going to be due to calcium and magnesium, and the other ions don't ever seem to matter. At least in every water sample I've looked at, iron has never been there high enough to contribute to as significantly to the hardness compared to the calcium and the magnesium. So what is the big deal about hardness? A lot of people freak out when they hear that their water's hard and they think their hair is going to fall out and they're going to die from all sorts of tragic illnesses. And the reality is, hard water is not bad for you for drinking at all. In fact, it has calcium carbonate in it and things like that, and that actually may alleviate a little bit of heartburn and some digestive issues. If the water has no calcium and magnesium in it, it often just doesn't taste right. It tastes bland, right? Too much calcium and magnesium can have a variety of effects. Most of it are kind of like physical on things. One of the big things that kind of drives everyone nuts is the scaling. So you can see here some pictures of the scaling here on a faucet or around a tap here around the sink, and that's just annoying. To a pretty high degree. I actually was just cleaning the other day in my kitchen and trying to get rid of some of that gunk. And you can do that actually with a vinegar water solution very easily. Vinegar will dissolve the minerals there and clean it up right away. And we have to do that once in a while around the house because there is hard water, which is like pretty much most places in the world, particularly Canada. Most of the tap water found in Canada is hard, at least to some degree. In some cases, this stuff can build up, and this is why usually given enough time, pipes will eventually start to form the precipitates in them. And this could take decades, but ultimately this is a reason why a lot of pipes eventually do burst because they're getting more and more constricted. And you can imagine the water pressure is getting higher as the diameter of the pipe is decreasing, and that's no fun. There's a lot of other kind of small effects to hard water. One of the things you can see is listed there is soap lathering. So hard water, it doesn't allow soap to lather quite as nicely, and some people are big on the taste of things. Sometimes if water's hard, let's say you make tea and it might look a little bit cloudier, or some people, like I said, particularly with things like tea and beverages, they often want soft water because they think it affects the taste. And I personally think the jury is out on that. Whether in terms of the taste, if you think about something like tea, you've got the taste of the tea leaves in there is going to overpower anything else. But anyway, it's a matter of preference. A lot of people have water softeners in their house for various reasons. Sometimes there's certain systems you might have that hot water on demand. People don't want it to get clogged up. It's an expensive system, so they have water softeners for that in some cases. But that's kind of the big deal about water hardness, is that it's contributing to the scaling, which can be a big deal on machinery or in things industrially. And of course, in your house, it's just kind of making a bit of a mess, and nobody likes that kind of thing. But health-wise, there's no evidence to suggest that this is bad. In fact, calcium and magnesium are an important part of your diets, so not a bad thing to have. Here is the classification scheme of hard water. I'll come back to this unit in a second, but you can see there's a classification scheme, and I think last time I tested it, the Fort McMurray water came out as about 200 milligrams per liter. So it was classified as very hard. This is actually what we're going to do tomorrow. We are going to test the water hardness of some water samples tomorrow, one of them being our tap water, and we'll find out what it is. And we'll measure this directly in the lab, and I'll come back to how we're going to do that in a minute. You can see that here is the big thing right here, is that calcium can be above 100 milligrams per liter in carbonate-rich rocks. So I'm not sure what all you cover in Neil's classes in terms of mineralogy and things like that, because I'm not really a mineralogist in terms of what is in the different rocks and all that. But this is one that I do know. I don't know if anybody knows what that is, but basically this is limestone. And so limestone is found all over Canada, particularly around here. We have limestone-rich rocks, and so as it rains, as water flows over the ground and all that, it's picking up calcium carbonate. And so this is actually probably the #1 biggest contributor to hard water is just limestone. Magnesium is found in different rock types. I couldn't tell you what type of rock types. I know very little about rocks, but all these things can be picked up from just, like I said, rain and land overflow and surface runoff and all that. These things are found abundantly in the environment. So it's probably no surprise they're found abundantly in our water. I'll come back to this thing here about how the units are milligrams per liter calcium carbonate. It used to be thought that hard water was all from calcium carbonate. And so the units here have kind of stuck. And so you'll see these units basically almost all the time. When we talk about water hardness, we talk about milligrams per liter calcium carbonate, even though it's not just calcium carbonate. There's magnesium in there, and the water hardness may be from other calcium minerals. But that unit has kind of stuck, which sometimes confuses people. Sometimes it's broken down between calcium and magnesium hardness as well in some classification schemes. Okay, so there are different ways to calculate hardness, but one of the standard ways to calculate hardness is to use Miller equivalence. So this is why it's good to know how to use Miller equivalence, because it's going to help us to calculate hardness. So if you take a look at this, we have some information about a sample of well water. So you can see we have 17 milligrams per liter of calcium and 8 milligrams per liter of magnesium. And so what we can do is calculate the hardness in this sample. Yes, I was going to do this on the board, and I didn't leave enough space here, so maybe I can cram it down there at the bottom somehow, and we'll do another sample in a second. Actually, let me just edit this PowerPoint for a second, and I'll make sure there's lots of space here. So just give me a second here. What I'm going to do is just fix that, and what I'll do is maybe I'll get a give myself a lot of extra space here by having a widescreen PowerPoint. So I'm just going to copy and paste that over here. Almost there. Okay, so just got to share that screen. So dependent on using the whiteboard usually for this particular class. Okay, so let's take a look at this. There's the problem there, right? So it tells you how much calcium we have here, how much magnesium. It's giving the equivalent weights. Okay, so the first step, we're going to do this in 2 steps. Okay, so step number 1, we'll call this calculating hardness. Calculating hardness. There we go. So step number 1 is we're going to calculate the mill equivalents per liter for the calcium and magnesium. So calculate milliequivalents per liter for calcium and magnesium. Okay, so let's do calcium. So remember our formula for calculating milliequivalents. I'm not going to write out the formula here just to make sure I have enough space for everything. But the formula is that you're going to basically take the milligrams per liter. So in that case for calcium, it's 17 milligrams per liter. And I'm going to divide it by the equivalent weight, which for calcium is 20 milligrams per milliequivalent. So notice my units for milligrams are going to cancel out, and I'm going to keep the milliequivalent per liter in the end. Okay, so we're going to calculate that. I'm going to punch this in my calculator, and I get 0.85. So here we go, 0.85, and the units are milliequivalent per liter. All right, let's do the magnesium. Okay, and the magnesium, it's the same calculation, just different numbers, 8 milligrams per liter. You'll see this is the trend. Usually magnesium has a bit of a higher, the calcium has a higher concentration than the magnesium. It's just a bit more abundant out there in the out in the wild. And the equivalent weight is 12.2 milligrams per milliequivalent. Okay, punch that into my calculator and I get 0.65. Okay. 0.65 milliequivalent per liter. So that is step one. Step two. Add them up. Add up the hardness, we'll say. Concentration. So that's basically the calcium plus the magnesium. So 0.85. plus 0.65, and the answer for that is 1.5 milliequivalent per liter. Okay, and then so step three is the last step. Step three is we need to convert that value, convert to milligrams per liter calcium carbonate. Okay, so remember our formula for calculating milliequivalents is taking the parts per million divided by the equivalent weight. Now we're back converting by using the equivalent weight of calcium carbonate. Okay, so I'll write out the formula for this. So this basically equals the concentration of the hardness in milliequivalent per liter times the equivalent weight of calcium carbonate, so CaCO3. Okay, so I'm multiplying those two numbers. So 1.5, oops, I'm missing the units over there, 1.5 equivalent per liter times the equivalent weight for calcium carbonate is over there, which is 50. That's a nice easy number to remember. And it's milligrams per milliequivalent. So take a look at that. You can see my units that cancel out, and I'm going to get my milliequivalent per liter are going to cancel out, and I'm going to get milligrams per liter. All right, looks like I left just enough space to put in the final answer, and it should be 75. So 75 milligrams per liter, and the full unit is milligrams per liter calcium carbonate. So just squeezing that in there. Okay, so we are going to do more of these sample calculations. All right, but just remember these three steps. Number one, you're converting the calcium and magnesium to the milliequivalent per liter. Number two, you're basically adding them together. So that's adding up the hardness from all the different components. If we had iron in there, we could do that as well. We would calculate the iron in milliequivalent per liter, and we'd add that to our total hardness. Iron would probably come out as 0.01 or something like that. So like I said, it's usually not that significant. And then lastly, you're converting back to milligrams per liter, but you're using the value for calcium carbonate. So if you take a look, this does match my answer here. You can see my answer there is 75.3. Probably when I did my calculation before, I probably was carrying more significant figures on my calculator, which ended up with the 75.3. The other thing I want to point out is this link here, and there's a lot of calculators there on the internet for calculating hardness by using your concentrations of calcium and magnesium. So I'm going to show you that particular calculator here. And I've got it loaded up here on Firefox. Let me see, where is it? There it is. So calculating water hardness calculator. Like I said, there's a whole bunch of these on the internet. I guess it looks like they have several calculators. It's telling you they have a slightly different definition of hard and very hard. The schema I showed you is the most common definitions. Anyway, it looks like they have their own scheme there, and it actually tells you a little bit about how to calculate it, and it's showing you a formula that kind of does some of the same things that we did in different types of steps. So in this case here, you can see I can basically punch in the concentration. So if you remember our concentrations from the problem, we had 17 milligrams per liter of calcium, the magnesium was 8, iron wasn't given, so you got to, I think, fill everything in 0 and 0. And notice if I actually look at the units, I could put in moles per liter as well. And then you just hit calculate, and then there's my answer, 75.3. So it's just doing the same math. Like I said, there's lots of calculators like this on the internet. And but unfortunately, you will need to know how to do this for test number 2. Okay, no urgent worrying about this yet, but test number 2, you will need to know how to do this for. Okay, so let me just get back to the PowerPoint. If I would do any other calculations, I might do the same thing, what I just did by putting it in a different slide. So here we go, back to here we go, and 75.3 milligrams per liter. All right, so yeah, here's one more calculation for us. We'll do another sample calculation. I'm not going to write out the steps like I did before, explain them. I'm just going to do 1, 2, 3. Okay, so let's try this one. This one has iron in it. You're going to see the iron isn't going to be probably not very significant at all. But let's give this one a try here. So remember, the first is to, step number 1 is to calculate the mill equivalents per liter. So we'll do that for calcium. So calcium, we got 40 milligrams per liter. I'm not even going to put the units in for you. 40 divided by 20. That I can do in my head. It's 2 mill equivalents per liter. Okay, magnesium. We have 10 milligrams per liter divided by 12.2. That one I cannot do in my head, so I'll have to grab my calculator for that one. So 10 divided by 12.2 is 0.82. And iron, so this time we have iron on there. Ferric. And so 0.1 divided by 27.9. Okay, so punch that in my calculator. 0.9. Okay, so this is 0.003536 if I round it, mill equivalent per liter. Okay, so remember number 2 is just adding those things up. So 2 plus 0.82 plus 0.0036. Okay, add all those up. And oops, okay, 2 plus, I probably shouldn't even need my calculator for this, do I? Because the answer is 2.8236. And of course, that is in mill equivalent per liter. So that's the amount of hardness. That's what I've done for the first 2 steps, is I've just calculated the amount of hardness, the total amount coming from all the multivalent cations. And then step number 3 is I'm going to take that and convert it back to milligrams per liter. So it's 2.82, and it's times the equivalent weight of calcium carbonate, which I didn't list on here, but it is on the previous slide, which is 50, what are the units? Milligrams per mil equivalent. So multiply 2.82 times 50, and I get 141. So 141 milligrams per liter calcium carbonate. So I'm hoping that is relatively straightforward. It's just a matter of remembering the steps, okay? There's kind of, a couple of things to remember. One is that you're basically figuring out, okay, calcium and magnesium, sometimes iron, that's what contributes to hardness, converting them to mil equivalents, adding them up to figure out how much the total amount of hardness. Sometimes, like I said, people will actually talk about calcium hardness or magnesium hardness alone. And in that case, you wouldn't be adding them up. And then you're converting to units of milligrams per liter of calcium bicarbonate. So this is probably the hardest math you'll see in this course, by the way, is dealing with the water hardness. And so if this is like the one thing you don't get, don't sweat it. In real life, people often use the calculators that you see on the internet. So I want to show you an example of a test question. And this is something we're going to be working towards for test number 2, okay? So test question, it's going to ask you all of these things, right? So you're going to have a water analysis, and you'll have all the ions in there: calcium, magnesium, sodium, potassium, whatever is found in that particular water analysis. And we've done all of these things here already. Okay, we've done calculating milligrams to mil equivalents. I've learned how to do the bar graph. We've learned how to do hypothetical combinations, and we've also learned how to calculate hardness. Alkalinity, we have not done that yet, and we're going to get into that shortly. I'm just not done talking about, quite done talking about hardness, because what I want to do is talk a little bit about today's lab, or tomorrow's lab, I mean, and then hopefully you'll have an idea of exactly what we are going to be doing tomorrow. So let's take a look at what we're doing in tomorrow's lab. In lab 1, what we're doing is basically a titration. So everyone has probably done at least a couple of titrations in their life by now. In Chemistry 101, you do 1 or 2 titrations. And most titrations that people are familiar with are acid-base titrations. So in an acid-base titration, you're adding, you're either adding, you have your burette and you have acid in there, or you have base, and you're neutralizing a base or an acid that's in your flask. And you're looking and you're watching for it to react. And usually there's an endpoint, and the endpoint can be measured by using a pH meter, or it can be used by using some sort of colorized indicator. Okay, so that is basically 2 things are reacting together, and there's a color change. And that's actually the basis of a lot of titrations. They don't all have to be acid and base type of titrations. And so in tomorrow's lab, we're going to use this compound here called EDTA. So EDTA is it's an acronym for a big long name. Let me see if I can say that. Ethylene diamine tetraacetic acid. Okay, that wasn't too bad. And that's what it looks like. It's a fancy little chemical there. It has some negative charges on it. And of course, negative charges are going to react with positive charges. So it turns out that EDTA reacts really strongly with divalent metal ions. So where have we seen that before? Well, we could have calcium, we could have magnesium, we could have iron. So those are all the things that contribute to hardness. And they react and they make this kind of, you can see this 3-dimensional structure here over on the right. That's what they do. And they do it in a 1-to-1 ratio. So this is kind of awesome, because 1-to-1 is awesome. We don't need to worry about stoichiometry. It's a 1-to-1 kind of thing going on. And all we need to do now is somehow figure out how we can measure this reaction. And it turns out that we have found a colorized indicator that is going to show us that this reaction is done. And so there's showing just the reaction of calcium with EDTA as a 1-for-1, magnesium with EDTA as a 1-for-1, right? So we have this indicator here. It's called Irochrome black. I'm not sure what the T is for, but that is the indicator we are going to use. And so you can see there's two colors, right? There's a reddish color and a blue color, okay? And so when there's calcium and magnesium in the solution, it looks red. So when there's calcium and magnesium, it looks kind of reddish color. And when all the calcium and magnesium is used up, it's going to turn blue. So hopefully everybody can see red and blue. If you have color issues, some people are colorblind, hopefully your partner is good at that. But that's basically what we're looking for. And this is the basis behind tomorrow's lab. Tomorrow's lab has a little bit of chemistry in it. So, you know, they're all calculations you've done before, and I'll go through them with you in the lab in terms of how they're going to work. Most people are going to need a little bit of a refresher, and that's why we're going to do the lab. I'm not going to do it all now until we've had a chance to kind of go through the lab and exactly what is going on. Because there's actually two steps for tomorrow's lab. One is we've got to standardize our EDTA solution. So that's part of the lab. And then we're going to measure the hardness in some water samples. And I think I have 4 water samples for tomorrow. We're going to measure a snow melt. We're going to measure tap water. We have some groundwater. I'm not sure which source of groundwater we have yet until I talk to the tech. And we have some, what I'm going to call is limestone water. So some water that has, it's basically, I made some artificial acid rain and dissolved some limestone in it. And hopefully we'll get some good results for those. The reality is, so this is what I'm seeing in the literature, right? This wine red and this inky blue. The reality is the real colors is this is a bit more what I'm seeing. So it's more of a paler pink and a lighter blue. But you know, I've seen different ranges and colors in this kind of exercise before. So just to show you what they should look like. So that's kind of lab 1. Like I said, this water hardness stuff is going to be the most difficult in terms of the math and calculations. So if you can get through and survive this part of the course, the rest of it, I guarantee you, is easier. Okay. But you know, we got to get some of this chemistry out of the way so we can understand a lot of the rest of the course too. All right, I'm going to keep going on unless there are any questions. And I want to talk a little bit about acidity and alkalinity, which is also part of tomorrow's lab. In particular, we're going to get a chance tomorrow to learn a little bit about pH meters, which is kind of a side project in tomorrow's lab. In this course, we're going to learn how to use all sorts of meters and devices. And a pH meter in some ways is the most basic and simplest one. It's easy to calibrate and really useful. And a lot of people use pH meters regularly. So a little bit about acidity, right? Water itself can also be an acid and a base, and I'm not going to get into all of that. In fact, there's a question here. Don't even worry about that. It's 1-to-1. But what I want to get into is what is pH. Okay, so pH. So notice it's a little p, okay, and it's a big H. So make sure you spell that right. Okay, that's one of my pet peeves in life. It's people who can't spell pH. Simplest thing to spell ever. The H actually stands for hydrogen, and P stands for power or potentia, which is like the Latin or something like that. Okay, so make sure you get that right. It's P, little p, big H. Okay, this is the formula for pH, and so you'll get a chance to try out this formula in tomorrow's lab. There's some sample questions there. I'm not going to grade the sample questions, but you will need to know how to calculate pH for test 2. So again, some more hints around test 2. But that's the formula, and it uses a log. Okay, and we'll do a couple of sample problems here in a moment. But let's talk a little about pH. You probably know a little bit about pH. People seem to talk about it a lot and have a general idea of what pH is all about. So which pH is neutral? So you probably know that a 7 is neutral. Okay, why are pH measurements important? There are thousands of reasons why pH measurements are important. It kind of depends what industry you're in. If water is too acidic or too basic, that can interfere with all sorts of chemical processes. If you're worried about something's chemistry, acidic and basic things can be corrosive, so they can be bad on machinery. In the food industry, the wrong pH can affect the taste and the health aspect of the food. So there's many, many reasons why pH is important. pH is important for healthy soils. pH is important for healthy water for fish and aquatic life. And it goes on and on and on. So it's a really important parameter of pretty much anything that's measured. And if you ever read anything in the field for environmental sciences, 9 times out of 10, you're going to be doing pH as part of that sampling process. Here's a couple of other things I've written down here. Biological systems, I guess I mentioned, reactivity of acidic things and corrosion and things like that. So lots and lots of reasons that pH is important. So here's a pH scale. There's a whole bunch of these you can find on the internet, but this one I really liked it for 2 reasons. It shows a lot of common things people might have in their home. So remember that pH 7 right here is neutral. And so a lot of our beverages that we might consume in the house are acidic or slightly acidic. So milk is around a 6.3. And most of our juices, orange juice and apple juice and things like that, are actually quite acidic beverages. And of course, famously, Coca-Cola and vinegar are acids, right? And you can see I like this as well because it talks a little bit about fish, right? And this is something we like to think about as environmental scientists, is how the parameters are going to be affecting the wildlife, of course. You can see on the basic part of the scale, you've got things like seawater. Seawater is about an 8.7 to 8.8, is pretty typical. Lots of detergents and cleaning chemicals have an alkaline or a basic properties to them. Okay, so I have some sample calculations here. I'm going to show you how to do this. Now, the hardest thing about doing these calculations for some people, quite honestly, it seems silly, but one of the hardest things is people actually understanding how to use their own calculator. So I encourage you, when you do your practice problems, do make sure that you understand how your calculator works, because sometimes things just get a little tricky when we're dealing with logs. I find with logs, every calculator is slightly different in terms of which order you press the button. Do you press log and then put in the number, or do you put the number and then you put in log? Sometimes you have to hit that shift function and so on. And so if you have problems with your calculator, let me know. When we do our tests in class, I'm going to be asking you to not use your phone calculator. You'll have to use a regular type of calculator. And so do make sure you understand how it works. So let's do these problems here. We'll do them one at a time, and I'll kind of just go through the steps and show you how these work. So here's the first one. So remember what our pH formula is. So pH is negative log of the hydrogen ion concentration. So it looks like that. So I'm basically just punching this into the formula, right? So negative log, and then, what did I do there? There we go. Negative log 2.3 times 10 to the minus 3. And that's kind of it. So in my calculator, I punch in the number. I punch in 2.3 times 10 to the minus 3. Then I hit the log button, and I actually get negative 2.6. But of course, there's a negative out front, so my final answer is 2.6. Okay, so that's kind of how that was done. Usually this part is a little easier than doing the reverse kind of calculation. Just keep in mind that this means this is acidic. And there should be no surprise here because we are dealing with a sample of vinegar. Okay, so I'll do those other 2 practice problems and I'll show you. And like I said, you get a little chance to do some practice problems with tomorrow's lab as well. So this one is asking for the exact opposite. In this case here, I have the pH of something and is asking for what the hydrogen ion concentration is. So here's my pH formula. I'll write it down for you again one more time. So pH formula is the negative log of the hydrogen ion concentration. Okay, so here goes a little bit of math for you in terms of if you remember how logs work. Okay, so in terms of how logs work, what I have to do is kind of flip things around. So I'm going to just basically, I'll start off by moving the negative sign, okay? And it's going to look something like that. And in terms of how logs work, here is how logs work. So remember, the log is kind of an inverse of an exponent. Okay, so that's what I'm doing. I'm taking that pH and I'm flipping it around and putting it to a power of 10. So if I write out the numbers on this, H positive equals 10 to the minus 2.6. There we go. So there's actually two ways for me to do this on my own calculator. And without having the calculator here, I can't exactly show you the buttons in terms of what is going on here. But generally, at this step here, what I do is or maybe sorry, this step here, I punch in negative 2.6 and I hit shift log. And so that gives me the inverse log of that. And the other way is I actually have 10 to the power button as well, that I can punch in 10 to the power and then put in negative 2.6. So again, something that is going to be, you have to figure out how to use your calculator on this. So when I do punch that in, I get 6.3 times 10 to the minus 7 moles per liter. Okay, and so this is, we would call this, I would not call this really, I would call this slightly acidic or mildly acidic. It's not very acidic. You can see it's not a 7, but it's kind of close to a 7, right? So this is not some water I'd be too concerned of in most circumstances. Okay, so one more calculation for us today, and then I think what I'll do is I'll probably wrap it up there. One more question. It's saying how many times more acidic is lemon juice than orange juice? Okay, so let's take a look at this. So let's do lemon juice first. What I'm going to do is I'm going to calculate out the hydrogen ion concentration. So remember, the hydrogen ion concentration, we just did this on the previous slide, is going to be is 10 to the minus pH. Okay, so lemon juice is 10 to the minus 2.3. And hold on a second, I'm just going to punch this in my calculator. Oh, something's going on with my calculator. Hold on. Maybe that's why I have a spare calculator here. Okay, let's try that again. Maybe I just didn't have enough light, these solar powered calculators, eh? Okay, so let me see here, 2.3 negative, oh no. Shift. Hold on a second. This other calculator works differently than my first one, so I have to remember how to use it. Okay, I clearly don't know how to use my new calculator. Anyone else have the number for me? I can't seem to find my other calculator seems to stop working, my main one. I don't know if I know how to do this on my phone. Let's see here. Looking for my other function here. 10. I think this is one of these Murphy laws things. When you do calculations in class, something goes wrong every time. Okay, well, I can't seem to do this on my new calculator. I have one other option. I might have one more calculator. Hold on a second. No, I don't have another calculator. Oh, somebody else has it for me. Yes, that sounds right. Thank you, Ellen. So basically 5.0 times 10 to the minus 3. That's moles per liter. Thank you very much. Like I said, you know, I'm not in my office, and sometimes that kind of messes me up in terms of having everything I need. Orange juice, we can do the same. And so this is 10 minus 3.3. And if I remember correctly, the answer here is 6.0 times 10 to the minus 3. So if you could confirm that I got that correct, Ellen, that would be awesome. But I'm pretty sure that's the case. And so if you take these two values, right? Or sorry, not 6.0.
Sorry.
Sorry, I got that. 5.0.
5.01 times 10 raised to negative 4. Negative 4.
I think is the correct value. So if you take a look at this, we have 5.0 times 10 to the minus 3 divided by 5.0 times 10 to the minus 2.
Mr. Blaine?
It's a 10 times difference, although I guess I put those upside down. That should be, in this case, 0.1. But I was asking for how many times more acidic is lemon juice than orange juice. I messed something up. I know I did. Yes, that would be why. 10 to the minus 4. Thank you again, Ellen. Ellen to the rescue. Sorry for the mess here on my slide. So 10 to the minus 3 divided by 10 to the minus 4. And the answer here is 10 times. Okay. So that one's a little bit more advanced, but just wanted to show you that if you look at this, we have a pH of 2.3 and a pH of 3.3. So remember that pH 3 is more acidic. And a power of 2.3 compared to a power of 3.3 basically means 10 times difference. So that's a big thing to know about the pH scale, is that it is logarithmic. And as you go down, when you go from 5 to 4 to 3, each time you go down an increment is 10 times more concentrated in acid or base. All right, looks like our time is up today. I'll probably do a couple more sample problems for some of these things next day. And other than that, I'll see everyone tomorrow, 9 a.m. Come to the chemistry lab, make sure you have everything that you need. And I look forward to seeing everyone in person. We'll see you there.